Welcome back to Calculus 2. In this lecture, we're going to introduce the second most important way to evaluate integrals with a method known as integration by parts. All right, so earlier in the course, we said substitution was the most important way to evaluate integrals. In this lecture, we'll get to the second most important method. So let's consider a concrete example here, evaluating the indefinite integral of x times e to the x. Now, we don't have many methods available to us yet. If we try a substitution, nothing seems to work. There's at least no obvious substitution I'm aware of. And unfortunately, we can't integrate each term. If you were to do that, integrating x, you'd get a half x squared. E to the x would integrate to itself. Unfortunately, finding antiderivatives, evaluating integrals, doesn't work that way. We can't integrate each factor and then multiply them together. Hence why integrating is so much harder than differentiating. Okay, so here we go. We have an example that none of our existing methods and techniques apply. So we need something new. That something new is going to be integration by parts. Now, in our lecture on substitution, we gave the foundation. We get integration rules by reversing differentiation rules. For substitution, we saw that came from the chain rule. Now, the product rule is going to lead to integration by parts. No surprise, the product rule is probably the second most important differentiation rule, leading to what we've been saying is now going to be the second most important integration rule. All right, so let's take a look at a short statement of the product rule, as you'd be familiar with from your Calculus 1 course. Pretty standard statement. How we're going to use this, instead of having the derivative on the left side of that statement, we're going to have an integral on the right side. And since we have this derivative statement, we already know what answer we would get for that integral. So if we reverse that, reverse the product rule, we get this. Not a kind of nice looking formula, but that is going to be the starting place for the well-known integration by parts formula. Now, this is the version that we're going to start from, but it's not going to be the version that we use in practice for integration by parts. You might have heard something about u and v and du, all these different quantities. We'll be getting to that, but this is not the version we'll use in practice. All right, well, let's build off of this. So we arrived at this by reversing the product rule. And what we're going to do is try to introduce notation that simplifies this a little bit. First thing I'll do on the left side is kind of rewrite that integral of the sum as the sum of two integrals. All right, we'll split it apart. And on the left side, that first integral of f prime times g, I'm going to reverse the order of multiplication and write that instead as the integral of g times f prime dx. Now, how we simplify this and turn it into a practical version, the familiar, well-known integration by parts formula, which we're on the verge of being able to state, is we basically introduce two substitutions. Substitutions are great ways in mathematics to kind of simplify kind of a lengthy or complicated looking expression and make it look a little more simpler or compact. So we're going to use two substitutions, u equals f of x and v equals g of x. Now, from what we covered with substitution, anytime we make a substitution, we have to calculate the appropriate differential or derivative. So u, we calculate du, with v, we calculate dv. These four quantities, u, v, du, and dv, those are the standard symbols in the well-known formula for integration by parts. Well, let's go ahead and use those symbols to rewrite the line right above, which is in terms of f, g, f prime, and g prime. So we're just going to make a replacement. We basically have the terms underlined here in red with what they get replaced with. And now we can just write down the formula simplified instead of having f and g everywhere, we have u and v, and their differentials du and dv. Okay, and what we get is this much more compact expression, the integral of v du plus the integral of u dv equals u times v. Now this is getting closer, but it's still not quite the familiar practical version for the integration by parts formula. What we do is basically subtract one of those integrals to the other side. And the standard version is we're going to subtract the integral of v du to the right side. And if we do that, we arrive at the famous, well-known integration by parts formula, the integral of u dv equals uv minus the integral of v du. What does that mean? So we'll be getting into that, but this is the version that we'll be using in practice. So if you want, pause the video, make sure to copy this down in your notes, since we'll be referring to this throughout the rest of this lecture, as well as the examples. All right, now before we move on, just to point out, since this is our first time stating this formula, the integration by parts formula is not uv minus the integral of v du. That is only the right-hand side. Some simple examples, the right-hand side is enough. Some complicated examples that we'll be getting to, you need to recall the complete formula. There is an integral, the integral of u dv, that's going to be our given integral on the left side. So always remember, there's a left side, the integral of u dv, and then equals the right side, uv minus the integral of v du. We'll recall the specific examples where that precise formula is necessary. All right, so here, let's just summarize. Here is our integration by parts formula. Through some of the writing in the notes, I'll just abbreviate this by IBP, indicating we're going to integrate by parts. And we have it there, u dv equals, or the integral of u dv equals uv minus the integral of v du. All right, now before we get to examples, let's go into detail about what we actually do with this. And we actually make two choices. We don't choose u and v. Notice on the left side, we have u and dv inside that integral. We make a choice for u, and we make a choice for dv. Now, whatever you choose for u, you differentiate to get du. And notice in the setup there, how I'll typically arrange the work when we go through a question. If we choose dv, we integrate to go back up to v. So you choose u and differentiate, choose dv and integrate it. That's how you get du and v. Now with that in mind, there's some tips and guidelines that will get you through probably the basic examples, but these are not like hard rules that you have to stick to. There'll be plenty of examples through this course and beyond where you would actually break these. But of course, in our introductory Calc 2 course, first learn the rules so that way later you can break them. All right, the first tip or guideline is we're going to choose u so that the differential du is simpler. Now, I don't have a precise meaning for what simpler means in this context, but think, for instance, u might be a power of x. The derivative would be 1 power less. That's somewhat simpler. All right, so u should give you a simpler quantity for du if you kind of chose correctly. All right, a second tip, due to how we calculate v, we have to integrate dv, is the second tip. You have to choose dv so that can be easily integrated. What we wouldn't want to do is choose dv so that way calculating v is as complicated as the question that we're working on, evaluating an integral. So usually dv should be a simple function that you can easily integrate or find an antiderivative for. All right, and then a third tip, probably the most important of all, is the integral on the right side. So you have uv minus the integral of v du. That integral should be simpler than the original integral that you're starting with. The original integral is what's on the left, the integral of u dv. These are guidelines which I want you to keep in mind through the basic examples. So pause the video, copy these down, that way you can have them in front of you. And right after this, we'll get to the first set of examples. All right, let's go ahead and proceed. Before we do so, just to follow up on the second tip about dv being easily integrated, recall what we might have called the 1 over a shortcut when we were integrating a basic function with a linear expression ax plus b inside. This shortcut is going to greatly speed up integration by parts questions. If your dv results in one of these integrals that you have to calculate, it might be several minutes of going through a substitution in detail. This will speed up your work considerably, provided you're comfortable with understanding where the 1 over a factor comes from. With all 4 of these tips, the 3 tips or guidelines, as well as this 1 over a shortcut for basic integrals, let's go ahead and get to some examples. Here we'll start with the intro example, finding the integral of x e to the x. This will be a kind of a simple one that will mention some of the basic guidelines and what could go wrong with them. So if you're curious and up for it, go ahead and pause the video and make an attempt at example 1. This is about as straightforward as it gets for an integration by parts question. We'll check in about a minute. Okay, so let's go through here. Remember, you choose u and you choose dv. So we're going to choose here u. Let's try u as x. The derivative of x, 1, is simpler. We'll choose dv as e to the x dx. Don't forget that differential. E to the x is easy to integrate. So these choices seem to meet our guidelines. Now we have to calculate du, and we have to calculate v. That should be straightforward. So du just becomes dx, or 1 dx, 1 being the derivative of x. All right, we have all 4 of our quantities here. Your integration by parts formula says this integral becomes uv minus the integral of v du. So we arrive at this. The uv term is x times e to the x. And now we have an integral, which you always get after integrating by parts. The integral of v du here is the integral of e to the x dx. Now that integral certainly is simpler than our original integral, since there's no factor of x on this. It's simpler also from the point of view, we know a basic antiderivative for the exponential function itself. So at this point, we're basically done. That integral of e to the x just evaluates to e to the x, and we're done. And there we go. Now, this first choice for u and dv worked. It met all the guidelines. I want to make sure you see what goes wrong had you made a different choice. Now, it's not wrong in the sense of being mathematically wrong. It's just wrong because it's going to make the problem harder, as we'll see. So let's take a look at a follow-up while we have this work on the screen, where we reverse our choice for u and dv. Instead of choosing u as x, let's choose u as e to the x. All right, what goes wrong here? This seems like the calculations are straightforward. du just becomes e to the x dx. And with v, or dv as x dx, we integrate that to get 1/2 x squared for v. All right, so we have all our pieces. What could go wrong? Well, we combine with the integration by parts formula, the integral of u dv equals uv minus the integral of v du. Now, this is all mathematically correct. There's no inconsistencies, but it's not a good idea. Take a look at your last integral there, the integral of 1/2 x squared e to the x. Our original integral was just x e to the x. Now, after integrating by parts, we've bumped the power up from x to x squared. So what we have done is something that makes the problem now harder. Instead of simplifying the problem, we complified it. If that's a real word, I don't think so. So this, while it's a mathematically correct choice, it's not a good choice in practice, since that integral has now become more complicated. Fortunately, our first choice, u as x and dv as e to the x, works. All right, let's go ahead and take a look at a second example. This one seems to be straightforward. I'd like you to make an attempt at this, but this is an important example. I'll give you a hint in your work with what you should find if you're on the right path. You're going to have to integrate by parts several times here. So pause the video, keep in mind, you're going to have to integrate by parts several times, twice, and we'll check in a few minutes. All right, welcome back. This one, I expect there possibly to be a lot of places where errors can creep in. Let's take our time going through this example. It'll kind of set us up for what comes next. So let's first get our choice for u in dv. Now, like the last example, we would not want to choose dv as x squared. If you chose dv as x squared, v would contain an x cubed. The power would go up. So if we choose u as x squared, du is 1 power less, 2x. So that's good. That means then if u is x squared, dv should be everything else, cosine of 2x dx. That is also easy to integrate. This choice seems to meet both our guidelines. All right, notice what I'm using going from our dv here, cosine of 2x, to v. It's the 1 over a shortcut that we mentioned a few minutes ago. Here, a is 2. The antiderivative will have a 1 over a, 1 over 2 factor. If the 1 over a shortcut isn't part of your regular mathematical toolbox right now in the course, definitely make it part, since here, that gives you a very quick way to calculate v. Otherwise, you'd have to go through probably a minute or 2 minutes worth of work with u substitution, if you're on top of substitution. All right, so we have all 4 quantities here. We combine with the integration by parts formula. The right-hand side becomes uv minus the integral of v du. Notice what I did there. V has a factor of 1/2. du also has a factor of 2. When you multiply them, 2 times 1/2, that cancels to 1. So just be careful with that. Simplify where possible. And that last integral now involves x times sine of 2x. That's going to be where the second integration by parts occur. Since we have a minus in front of that integral, and we're going to apply the integration by parts formula again, which again has a minus in it, we might incur a double negative, minus a negative. So be careful, put around that integral after integrating by parts the first time a set of parentheses or brackets. One of the biggest tips I can advocate in kind of going through tedious calculations. All right, so the integral in the brackets, we're going to apply integration by parts again to that. So here I'm just writing that down again, just for ease of calculation. And I have the work for what you would choose for that integral with your u and dv. Now what you don't want to do is reverse your choice of u and dv from what you made first. We chose u as the power of x. We want to still choose u as the power of x here. If you switch your choice for u and dv in this second integration by parts, you could literally undo all of the work you just did and get back to where you started. So be consistent with your choice for u and dv throughout a problem where you might have to integrate by parts several times. All right, the calculations here are not too bad. Now, within the brackets for that integral, we apply the integration by parts formula again. That integral in the brackets now becomes equal to your second choice for uv minus the integral of v du. With that second choice, that quantity in the brackets applying your integration by parts formula, the right-hand side now becomes uv minus the integral of v du. Now, I want to point out a sneaky little calculation I did here. You might see it. Our integration by parts formula involves minus the integral of v du. Notice in this second choice for v, there's a minus. That's going to lead to minus a negative. Be careful, you can cancel that as I did here. Just be careful. One minus comes from the integration by parts formula for the second time. The second minus comes from your second choice for v, which also has a minus or negative. So just be careful with that. Sign errors are one of the biggest source of errors for students. All right, now at this point, the second integration by parts still leaves you with an integral, the integral of 1/2 cosine of 2x. Fortunately, by integrating by parts twice, there is no more power of x on that last integral. Notice each integration by parts, the resulting integral has become simpler and simpler, 1 power less. If you evaluate that last integral, the integral of 1/2 cosine of 2x, you get another 1 over a factor, another factor of 1/2. The existing 1/2 there times 1/2 becomes 1/4. And then the antiderivative for cosine would be sine. All right, the rest of it is just cleaning this up. We have a minus in front of the brackets. We can distribute that in and change some signs. Some of the negatives cancel out. And we arrive at our answer here, 1/2 x squared times sine of 2x plus 1/2 x cosine of 2x minus 1/4 sine of 2x. And of course, don't forget the plus c, otherwise it'd be like minus 1,000 points. Okay, this one was, pretty tedious. We're creeping into the moderate to difficult problems. No surprise, since there was an x squared in this original integral, that we ended up integrating by parts twice. It'd be nice if there was a shortcut, right? Well, there is. There's a shortcut that I've had passed down through the Anderson family generations here, known as the tabular method. And this is a shortcut for repeated integration by parts. Now, it's not going to apply to a lot of problems, but the integrals where it can apply can be evaluated extremely quickly. They're of the form a polynomial, or just a single power of x, times either e to the x, sine of x, or cosine of x. Those are three standard functions that pop up a lot within mathematics, science, and engineering courses. So the notation here, p of x, is some polynomial, maybe of degree n. All right, now how the tabular method works, what it does is it speeds up your calculation of the repeated integration by parts. So this is called the tabular method since we set it up in the form of a table. All right, we have three columns. We have a column for u. In that column for u, we're going to successively differentiate. Remember, with u, we differentiate to get du. And then in the rightmost column, we have dv. That column, we're going to successively integrate. Since when we choose dv, we integrate to get v. Now, in this setup, let's take a look at where some of the integration by parts formulas terms come from. Diagonal there, we have dv in that top corner of the table. Below that would be the integral of dv, v. So it's your diagonal there that represents the uv term. So we're going to see something about the diagonals come into this, the diagonal products. Those are your uv terms. The benefit of using the tabular method is if the expression p of x is a polynomial or a power of x, you can successively differentiate that to eventually get 0. So think of any power of x, you can differentiate it, and eventually you'll get down to 0. All right, so the tabular method just speeds all this up. We just repeat that. The leftmost column is alternating signs. Now, where do the alternating signs come from? Well, we basically saw that in example 2. The first integration by parts gives you minus the integral of v du. Maybe that integral of v du has another minus in it. Minus and negative cancels to a plus. So we have alternating signs. This kind of automatically accounts for that with repeated integration by parts. All right, we always start it with a plus and then alternate down. Now, how we extract our answer here is we add all of the uv terms, which are the signed diagonal products. We multiply the sign across to u and then diagonally down to dv. We sum all those up, all those terms, the signed diagonal products would be part of your antiderivative. Now let's go ahead and apply this to example 2. Maybe pause the video if needed, so that way you can copy this. I realize, as we pointed out here, it might not be apparent how you set up the tabular method. But let's take a look at that in example 2, which we'll revisit. All right, so we'll evaluate the same thing, the integral of x squared cosine of 2x. We still make the same choice for u, x squared, same choice for dv, cosine of 2x. Pause the video and see if you can quickly complete the table and extract your answer for the antiderivative. We'll check in about a minute. All right, welcome back. Let's complete the table here with our choice of u equals x squared. We're going to successively or repeatedly differentiate that. All right, the first derivative will become 2x. 2x differentiates to 2, and then 2, a constant, differentiates to 0. The dv column, we repeatedly or successively integrate. That's a little bit trickier since we have trigonometric antiderivatives here. Notice I'm applying the 1 over a shortcut since we have cosine of 2x. 2x is a linear expression. All right, hopefully that work goes quick. If you're on top of the 1/a shortcut, that probably greatly assisted here. We just have to now extract our answer. We multiply the sign across to u and then diagonally down to dv. Then we just sum all those terms up. And we arrive at the same answer. This is probably a little quicker in practice, but it's not as universal as our standard basic integration by parts formula. This is a kind of a special case for what happens typically in calculations for integrals within science and engineering courses. All right, now I do want to take a look at one last example, just so you can kind of practice and refine applying the tabular method where applicable. Recall basically a polynomial times an exponential, sine, or cosine. So let's take a look at one last one here. Integrate x cubed e to the 2x. You can probably see here, due to x cubed, you'd have to integrate by parts, not once, not twice, but thrice, 3 times. Well, who wants to do that? Apply the tabular method. You might be able to solve this integral in 30 seconds with the tabular method. We'll check in momentarily. Okay, let's go ahead and apply the tabular method here. You would start your choice for u as x cubed, dv as e to the 2x. If you go through and set up that table very quickly, you should get this. Since every term has e to the 2x in it, I just factor that out. With practice, you can probably solve this integral with the tabular method in probably 20 to 30 seconds. This is it for part 1 of our lecture on integration by parts. We're going to immediately jump to part 2, where we'll get into kind of some more complicated examples and how we incorporate definite integrals.